this video, we're going to talk about the null space of a matrix. The null space of a matrix. So to provide some context, we've talked about subspaces of Rn and a basis for a subspace and the dimension of a subspace. When we're talking about subspaces of Rn, those have nothing to do with matrices, right? I mean, you can use matrices, it turns out, to say something about the dimension of a subspace, but in terms of what they are, they really have nothing to do with matrices. But we'll see that if you have a matrix, if you start with a matrix, any matrix, there are subspaces that you can make from that matrix. And there are three subspaces. One of them is the null space, one of them is the column space, and one of them is the row space. In this video, we're going to talk about the null space of a matrix. Okay, so every matrix has a null space. And what is the null space? Let's look at the definition. So let's say you have a matrix A, just an n by n matrix. The null space of a matrix A is defined to be the set of all solutions to the equation AX equals the zero vector. Okay, so it's all of the vectors x such that when you do A times x, you get the zero vector. So for instance, let's say that A is 3, -2, 6, -4. Okay, let's make this a bit nicer. Is the vector 2, 3 in the null space of A, and let's write it null of A. I mean, it depends on, there's no standard notation for the null space, but this seems like an okay notation. In null of A, in other words, is this an element of null of A? Well, how do we know? Right, we have to use the definition. It would be in the null space if A times that vector is the zero vector. So if you multiply it and you get the zero vector, it's in the null space. If you do A times that vector and you don't get the zero vector, then it's not in the null space. So let's multiply. If you multiply them, you get, okay, the first component is 6 minus 6 is 0. The second component is 12 minus 12 equals 0. So the answer is yes. Right. Because when you multiply them, you get the zero vector. On the other hand, is 1, 1 in the null space? Well, the answer is no, because if you multiply A by 1, 1, you do not get 0, 0. In fact, the first component is not even 0. It's 3 minus 2, which is 1. You don't even need to know what the second component is. You know that you're not going to get 0, 0. But anyway, you're going to get 2. Right? And this is not the zero vector. Okay? So the first thing we want to make sure of is, how do you know that this set of solutions is actually a null space? So here's the theorem. Is a subspace. So the null space of any matrix, so let's say m by n matrix is a subspace of R. Now, do you think I'm going to write M or N? It's N. Because when you have an M by N matrix, the vectors that you do A times that vector, okay, the input vectors are in Rn, right? And when you do A times, if you have an m by n matrix, you can multiply it by an n by 1 matrix, so that vector has n components, and then the result will be an m by 1 matrix, so that's a vector with m components. So the null space is a subset of Rn. But we're trying to say that it's a subspace of Rn. So what do we need to do? Well, we need to show that, first of all, it's non-empty. In other words, there's actually something in the null space. Well, so here's the proof. So the null space, let's call the matrix A. Then we know that the null space contains the zero vector in Rn, right? Because A times the zero vector is the zero vector, right? So the zero vector is in there. Subspace is non-empty. The subset is non-empty. And now we need to check closure under vector addition. So for closure under vector addition, what do we need to do? We need to start off with two vectors in the null space and show that when you add them, the result is also in the null space. That's what closure under vector addition means. So suppose that V1 and V2 are elements of the null space of A. So we need to check that V1 plus V2 is in the null space of A. We need to check that V1 plus V2 is in the null space of A. Now remember, saying that the vector is in the null space of A is just another way of saying that when you do A times that vector, you get the zero vector. So we know V1 is in the null space of A. That means that A times V1 is the zero vector. And V2 is in the null space, so A times V2 is the zero vector. Right, the zero vector in Rm. And we want to check that when you do A times V1 plus V2, you get the zero vector. Well, A times V1 plus V2, what can we do here? We can distribute the A across, right? That's a property of the matrix multiplication. This is A times V1 plus A times V2. And A times V1 we know is the zero vector because V1 is in the null space, and A times V2 is also the zero vector. And when you add the zero vector and the zero vector, you get the zero vector. So therefore, okay, so V1 plus V2 is in the null space because when you do A times it, you get 0. And finally, okay, maybe I'll put bullet points. So this first bullet point shows that the zero vector is in the set. The second point is closure under vector addition, and then the final thing we need is closure under scalar multiplication. So what does that mean? It means that we need to start off with a vector in the null space of A, and we want to check that every scalar multiple of that vector is also in the null space of A. So let C be a real number. Then we need to check that when you scale V1, oh, we don't even need the 1, we can just call it V because we only have one vector. Okay, so suppose that V is in the null space. Let C be an R. We need to check that CV is an element in the null space of of A. Well, again, a lot of this is just unpacking the definitions and using a property of matrix vector multiplication. So we know that since V is in the null space of A times V is the zero vector, and we need to check that when you do A times CV, you get the zero vector, but A times CV is just C times AV, right? That's a property of matrix vector multiplication. You can pull out the scalar, and then A times V is the zero vector, and so this is C times the zero vector, and when you scale the zero vector by any constant, you get the zero vector. So therefore, A times CV is the zero vector, which means that CV is in the null space. And so therefore, the null space is in fact closed under scalar multiplication, and so we prove the three things that we need to prove, that this set, the null space, is non-empty. That's the first thing. And then the second thing, that's closed under vector addition and scalar multiplication, and therefore it is in fact the subspace of Rn. Okay. Now let's look at some specific examples of a null space. We've seen that it's easy to check whether or not a given vector is in the null space or not, but how do you actually say what the null space is? Well, essentially what we need to do is we need to solve AX equals 0. So let's look at some examples. So what's the null space of this matrix A, which is the first column is 1, 2, 3, and the second column is 2, 3, 4. What's the null space of this matrix? Can you see what it's going to be without doing any computations? When you look at these two columns, what do you notice about them? They're linearly independent, right? They're not parallel. And so what's the solutions to AX equals 0? The solution to AX equals 0 is just X equals 0. It's the set consisting of 0. So this is a one element, this subspace has one element, the 0 vector. And by definition, this has dimension 0. So we consider the 0 subspace to be 0 dimensional. Okay. So this is 0 dimensional. So null space of A is 0 dimensional. For this subspace, just consisting of the 0 vector, it's a bit complicated to make sense of linear independence and spanning. So technically, I don't want to get too wrapped up in what exactly is the basis for the subspace. By definition, it turns out that we would take the basis to be the empty set. Okay, but I don't want to get too carried away by that. We just define the dimension to be 0. Dimension of the 0 subspace. Okay, let's look at another example. So what's the null space of this matrix, where the columns are 1, 2, 2, 3, and 3, 4? Well, we need to solve AX equals 0, right? Because the null space is the solutions to AX equals 0. So we solve AX equals 0, and since we're solving a homogeneous equation, we don't actually need to augment the matrix. If you row reduce the matrix, let's see, so we're going to do row 2 goes to row 2 minus 2 row 1, and if you do that, you get 0, minus 1, negative 2. And this is in echelon form. So now I see my free variables and my pivot variables, so to speak. The leading variables, I have a pivot here and a pivot there. So let's just use x1, x2, and x3 as my variables. So I see that x3 is free, right? Should I just write this down? Leading variables are x1 and x2. x3 is a free variable because this third column doesn't have a pivot. And so we set x3, say, equal to t. And, oh, we should probably get this in reduced row echelon form, right? To make it easier for ourselves. So if you calculate the reduced row echelon form, I'll skip the steps, but you scale row 2 by -1, so you get 1, 2 on the bottom, and then you do row 1 minus 2 row 2. And when you do that, you're going to get this. So this is the reduced row echelon form of A. Right? And now it's easier because this first equation, right, this is a homogeneous equation. This says that x1 minus x3 is 0. So x1 minus x3 is 0. Second equation says x2 plus 2x3 equals 0. And we set x3 equal to some parameter t. And so you get that x1 is equal to x3, x2 is negative 2x3, and x3 is just 3. X3 is just x3, right? And so this, when you rewrite it, is saying that x1, x2, x3 is equal to t times 1, negative 2, 1. And so therefore, right, this is the null space. We're solving ax equals 0, and we saw that the solution is all scalar multiples of 1, negative 2, 1. And so therefore, the null space is one-dimensional. The null space of A is one-dimensional, and it's spanned by the vector 1, negative 2, 1. And right, so a basis is just the set consisting of 1, negative 2, 1. Okay, so let's draw a little picture. So we have, okay, so here's R3, and we have 1, negative 2, 1. So let's say it's, okay, let's just call this vector V1. Or let's just call it V because we only have one vector. So if you call this V, call this V, then okay, 1, negative 2, 1 is maybe here. So here's V1, and whenever you take, okay, I want this to go to the origin. Okay, so something like that, just pretend it's a straight line. There you go. The span of V1, right? That's the null space. So all these vectors along this line through the origin, those vectors, when you do A times it, all go to the 0 vector. So that's the null space of A. It's that line. And A is this 3 by 2, it's a 2 by 3 matrix. And so, A is taking these vectors and spitting out vectors in R2. And basically what's going on is all the vectors on this blue line are going to go to the origin. Here. That's the origin. If you plug in any vector along this line, right, any vector whatsoever, and you do A times it, you're going to get this, the origin. That's what the null space is. Okay, and now notice, if you think about it, right, in this example, the dimension of the null space was how many free variables you have. There is one free variable, and that gives you there was one free variable, x3, and that gave you one parameter, t, this parameter t. Right, so this was because there was one free variable. And it turns out that this is generally true, that whenever you have a matrix, the dimension of the null space is how many free variables you have. It's how many non-pivot columns you have. That turns out to be a general theorem. That's called the rank nullity theorem. So the dimension of the null space of A is always the number of non-pivot columns, or the number of free columns of the matrix. Okay? So in general, yeah, that's what you would do. You would solve, to find the null space of A, you solve Ax equals 0. In the next video, we'll do some more complicated examples of how to find a basis for the null space of A. But hopefully this video just gave you a good idea of what the null space even is, and how to calculate it in some simple examples.